Okay, so let's go ahead and learn how to solve linear programming problems by the geometric or graphing method, which is basically what this section covers. Start with an application. This ring company sells two types of rings. We have the brass ring and the aluminum. Now, we're given that they can produce up to, that means they can't produce more than that, 24 rings each day. And they can use up to 60 man-hours for labor per day. So that just means they can't go over these numbers. And now here it says it takes 3 man-hours to make a brass ring and 2 man-hours to make an aluminum ring. How many of each type of ring should be made daily to maximize the company's profit if the profit on a brass ring is $40 and the profit on an aluminum ring is $35? Okay, now this problem, we do have the information to get an objective function, but we'll get to that in a minute. You can set up a table on these. So if you read, always look at the question, and it generally will tell you what the variables represent. Notice it says how many of each type of ring. So I'm going to let X be the number of brass rings, and I'm going to let Y be the number of aluminum rings. Now, I've got two conditions that have to be satisfied. I have to stay within a total of 24 rings per day, and I have to stay within a total of 60 man-hours per day. So I know that the total number of rings I produce must be less than or equal to 24, and the total number of man-hours must be less than or equal to 60. Well, let's talk about the number of rings. That's the easy part. All you have to do to get the total number of rings produced is just add X and Y together. So that's just 1X plus 1Y, or more simply, X plus Y. And so X plus Y must be less than or equal to 24. Now, the actual hours, if you have to look at this sentence, it says it takes 3 hours to make a brass ring and 2 hours to make an aluminum ring. So for each brass ring, it's going to take 3 hours. So 3x is the total time in making brass rings, and each aluminum ring takes 2 hours. So 2y is the total hours for aluminum rings. And so that means the total man-hours to make brass and aluminum rings together would be 3x plus 2y, and that has to be less than or equal to 60. And then, of course, you can't make a negative number of rings, so both x and y have to be greater than or equal to 0. And then last, the objective function. This is the function we wish to maximize or minimize, but in this case it's maximize. We want to maximize our profit, and in the last statement here, it says the profit on each brass ring is $40 and each aluminum ring is $35. So that profit function would be profit equals 40x plus 35y. When we put all this together, we get a linear programming model. And what I'm putting in this rectangle right here is what's called the linear programming model. So if you're asked to set up a linear programming problem or create the linear programming model, this is what they're asking you for. You identify whether you're maximizing or minimizing, and then you identify the objective function. You identify the problem constraints. In this case we have 2, and then don't forget that you have to include the non-negative constraints, and that's how you set up the problem. Well, then the next step is to solve this problem by the graphing method. So to solve this, we need to graph x plus y is less than or equal to 24 and 3x plus 2y is less than or equal to 60, and find where they overlap. So we've done this before earlier in this chapter. So to graph x plus y is less than or equal to 24, we graph the boundary x plus y equal 24, and we can easily find the intercepts 0, 24, and 24, 0. Okay, so this goes through Okay, so this goes through 0, 24 and 24, 0. So here's the point 0, 24, and here's the point 24, 0. And if you'll see the blue line represents the x plus y equals 24. Okay, so now if we were to test the origin, which is down here, so if we tested that origin and plugged it in, we would get 0 is less than or equal to 24, which is true. So that means we would shade everything below this blue line. And that would actually give me some of this up here, right there. Now, the other line, 3x plus 2y is less than or equal to 60, its boundary is 3x plus 2y equals 60. And you can find its intercepts. If x is 0, y is 30. If y is 0, x is 20. So it goes through this point up here, 0, 30. And it goes through this point right here, 20, 0. So I draw a line through there, okay? And then, again, I test this point 0, 0 here, and I get a true statement. 0 is less than or equal to 60. So in that case, I would have to graph everything below this line. Okay, so that would be this region here. Okay, so let's see here. I have to stay underneath that red line. Okay, so now if you look for the overlap, everything below the red line overlapped with everything below the blue line. Let me just show you what you'll get here. Get rid of some of this stuff. Okay, so what you're going to get is you're going to be bounded here by the blue line, and then right here where the lines intersect, it's going to change boundaries, and you're going to be bounded by the red line. And then you're going to have everything below those two boundaries as your region. But what we have to do after that is we have to remember that these two inequalities restrict us to the first quadrant. So technically we have to cut out anything that's below the x-axis and anything that's to the left of the y-axis. So basically we just get this region in here. And over here I've got it drawn for you a little bit better. So I've shown you the bounded region. I've got it in this black boundary here so that you can see the region. So it's this green region that falls within these black boundaries. So if you look at this, you know what three of these corner points are. 0, 0 is the corner point at the origin, and this is the point 0, 24 because we got that from over here, and then this point is 20, 0. We got that from over here. And then what you have to do to get this point is you actually have to solve this system of equations, x plus y equal 24 and 3x plus 2y equals 60, so that you can find where those two lines intersect. And when I solved it, I got 12, 12. So the corner points here are 0, 0, 0, 24, 12, 12, and 20, 0. Now, there's a discussion down here about why we only check the corner points, but I'm going to leave that for you to read, and I'm just going to go on down and just plug in the corner points. So, yeah, here it is. So actually, the objective function, remember, was 40x plus 35y. So if I plug in 0, 0, obviously I get a 0 profit, which that makes sense because if you don't manufacture anything, you're not going to get a profit. And then the other one of the other corner points was 0.24. If I plug that in, I get 40 times 0 plus 35 times 24, which gives me 840, which is better, obviously better than 0. If I plug 12 in, then I get 40 times 12 plus 35 times 12, and that's going to give me $900 profit. And then if I plug 20 in, I'm going to get 40 times 20 plus 35 times 0, which is $800 profit. So if you compare these four values, you're going to see that your optimal solution is a maximum here, right here, of $900. So the maximum is going to be a profit of $900, and it occurs when x is 12 and y is 12. And so that's where it occurs. And by the way, this was a bounded region up here, because it's a bounded region because I can draw a circle around it. If you can draw a circle around it, it's a bounded region. And remember, a bounded region has both a maximum and a minimum. We weren't really concerned about the minimum here. The minimum's 0, but that's not what we were concerned with. We wanted the maximum. So that's how you solve a linear programming problem geometrically. Okay, you can read the notes leading up to this example, but I'm going to go ahead and just pick up here. Basically, we should be able to speed up our process a little bit. Here we're maximizing this objective function. We're given these two constraints and our non-negative constraints. So if I wanted to graph this problem or graph this system, I would have to graph the boundary x plus 2y equals 32, which goes through 0, 16, and 32, 0. So that's there. And 32, 0 is actually way over here somewhere off the graph. And then the other one, if I let x be 0 and solve for y, I get 21 for y. If I let y be 0 and solve for x, I get 28. So this one goes through 0, 21, which is actually up here somewhere, and 28, 0, which is right here. Now, the first line, the first one, if you graph it, 0, 16, and then follow it down to 32, 0, which is over here, you're going to get that line. And then when you test the corner point 0, 0, or the origin 0, 0, you're going to get a true statement. So you shade everything below this line. So basically you shade everything below that line. And then the other line that goes through 0, 21 and 28, 0 would be this line. And then if you test 0, 0 for that line, you're also going to get a true statement. So you shade everything below that line as well. So if you take the overlap between everything below this line and everything below this line and stay in the first quadrant, because x and y has to be greater than or equal to 0, so you stay in the first quadrant, then basically you're going to be bounded. You're going to be bounded here, and this is not perfectly straight, but I think you'll get the picture. You're bounded there, you're bounded there, and then you're going to be bounded up here. So basically you're getting the region, you know, inside here. And you have four corner points, 0, 0, 0, 16, 28, 0, and then you can get 26 by solving this system of equations, and that'll tell you where the lines intersect, which is 26. Now, the objective function was 20x plus 80y. So if I plug each of these corner points in to that objective function, you can see that I'm going to get, well, I'm sorry, that's not the original objective function. Here's the original objective function. If you plug everything into the original objective function, you're going to get a maximum of 1480 at the point 26. But down here I'm just showing you if we had changed the objective function to something different, then the maximum could occur at a different point. So if the objective function had been 20x plus 80y and you plug in all your corner points, then you would get the maximum of 1280 at the point 0, 16. And all that means is that sometimes it's better not to produce a particular item. So in this case, you produce none of the x items and 16 of the y items.